Okay, so welcome again in the next part of our video series on refraction of light. In previous videos, you have learned what I have written on the screens right now, that how refractive index is defined, how it is a relative term and also an absolute term, right? So let's move further. Let's move further with our refraction. Okay. Now I want to tell you that this particular law that we have written, okay, both of them, relative also and absolute also, is called Snell's law. It's called Snell's law. That's something that I should tell you because it directly comes into exams. So yeah, you should remember that. Now to the important part, that this angle I, that was incident angle, and this angle R, that was the refractive angle, are limited to some values, and what are those values? Those values are 0 degree to 90 degree. That these values can only change from 0 degree to 90 degree, or we can say this Snell's law upholds to the values that are 0 degrees, that are between 0 degrees and 90 degrees. Okay, and now how do we explain that? So to explain that, I have loaded up a simulation for you guys. A simulation is nothing but an experiment that is simulated for you guys to understand the concept better. Okay, so we have a glass sheet here, we have air, and we have our torch that acts as a light source. Okay, let's not wait and just turn on this light. Okay, and you see the beautiful refraction, right? You can change this material to be water, you can change this material to be oil, you can change this material to be diamond. Okay, such beautiful refraction happens in these particular materials, yeah, this particular medium, right? Now I can change the angle, by which I shine my light, okay, and then the respective refraction angle or refractive angle also changes, right? Now what happens if I approach this angle to 0 degree, right? The incident angle to 0 degree, this 0 degree, this I, that is incident angle, is 30 degree right now. Now if I change it to be a bit less, okay, 24 degree, okay, 16 degrees, okay, 8 degrees, 5 degrees, 2 degrees, and 0 degrees, the light just passes through. The light just passes through the material. It doesn't refract at all. How cool is that? No matter which material you take, the light just passes through. It doesn't refract. And how do we explain that? How do you know? How can you calculate that? So it is very easy. Let's say we have glass, right? We have glass as our medium, and for glass we have the reflective index, the absolute refractive index, around 1.5. So this Nm is 1.5, right? Now the incident angle that we controlled, we changed the light source, right? The incident angle, we put it to 0 degree. We put the incident angle as 0 degree, and we want to find the R, the refractive angle. How much will it refract, right? So we can say that sine R will be equal to, you all know from your math textbook that sine 0 is 0 degrees. Sine 0 degrees, the value of it is 0. So 0 by 1.5 would be 0. And for the value of 0, what would the angle R be? It would also be 0, right? It would also be 0. You can see that from the table that is there in your mathematics textbook, okay, which tells the values of sine, cos, etc. Okay, so this mathematically tells us that if you incident the light in a medium, on a medium at 0 degree, it won't refract at all, and that's what we saw in our simulation as well. That it just passes through. How amazing is that? Okay, so 0 degree limit is done. Now we talk about the 90 degree limit. Let's move to another simulation, a bit more advanced simulation that has a whole protector and everything to see the angle precisely. Okay, now let's set our laser pointer and let's turn it on. Okay, now we see a refraction, but what is that? What is this faint light? What is it? It is the reflection of light. Now you might say, we are learning refraction. What is reflection doing here? The nature doesn't care about the categories. The nature doesn't care. Both of these things happen simultaneously. Refraction and reflection happen simultaneously. Okay, it doesn't matter that we only show refraction sometimes, but in reality both of them happen. So if I move this laser pointer to larger amount of angle, then the refractive angle changes, right? And oops, the refraction is completely gone. The refraction is completely gone, and the only thing that's happening is reflection. Okay, refraction is completely gone. So for flint glass, you cannot even increase the angle over 40 degree to observe refraction. Okay, let's change the material. Let's say crown glass. Okay, it's kind of same for it. Let's say quartz. For quartz we can increase even a bit more, but okay. And for diamond it is even less. It's very less, right? Like 25 degrees or something. Okay, so don't talk about 90 degree. The refraction is disappearing even much before than 90 degrees. Theoretically you can extend it till 90 degree if the material is different, but for the materials that we have around, the typical materials that we find, the angle stays well below 90 degree, even well below 45 degree, and refraction completely disappears. And only reflection remains. So if we cannot observe refraction, how do we even measure the angle of it? Okay, so that was about the limits that we have over our angle. Okay, let's move. Okay, so there is a particular diagram that shows rare material and dense material. Do we mean when we say rare material or dense material that glass is dense and air is rare? Do we mean this? No, we do not mean this. Mass density and optical density are different things. You can read about this more on 149 page, and there is more to know section. You can read about this and get more knowledge about this, but I will just explain this to you. That doesn't mean that if a material has more density, mass density, then it will be more optically dense. And there is an example. Here that ruby crystal has the refractive index as 1.71. So it is less than diamond, which has 2.42 as its refractive index, but the density of ruby is more and the density of diamond is less, right? So optically, if we say optically, then optically rare and optically dense are not as same as mass dense and mass rare. You can read more about it, and I will highly encourage you to read more about it on the 149 page of your science textbook, and there is more to know section. Okay, let's move to the questions. Yes, my favorite part. So we have this question that a ray of light traveling in air and enters obliquely into water. Does the light ray bend towards the normal or away from the normal, right? Like intuitively we know that our light bends towards the normal. Oops. Our light bends towards the normal, right? It's going towards the normal. Okay, but why does that happen? Okay, if we have glass here, this is glass, right? This is glass. So if this is glass, then this is glass, then why does that happen? Okay, so now we can say for why answer, we can say that to answer this why question, we can say that glass is a denser medium. Glass is an optically dense medium, and glass is optically denser than air. Okay, this was air and this was glass. So because it's optically denser, the light will bend towards the normal. And when light leaves from glass, you can see when light leaves from glass, you can see because air was optically rarer. Air is optically rarer. Okay, I can just okay, air is optically rare. Air is optically rare. So this particular light ray bent away from normal, right? It bent away from normal, and in this case it bent towards the normal. Okay, I hope that is clear. Next question was, light enters from air to glass having refractive index 1.5. What is the speed of light in the glass? The speed of light in vacuum is 3 into 10 raised to 8 meter per second. Okay, it is given that N2, that is basically N21 where 1 is nothing but vacuum, right? When 1 is nothing but vacuum, that's how we defined absolute refractive index, right? So we can write sin I by sin R, or we can write V1 by V2. Okay, the question asks about this. So it says that in vacuum our speed is this much, and we had to find V2, that is the speed in glass, and the refractive index that is given is 1.5. so you guys can calculate it and tell me the answer in the comments, right? Okay, let's move to the next question. Which is, okay, we can just do it because the calculation is quite easy. 1.5 by 3 into 10 raised to 8 would be 1 by V2, and then V2 will be 3 by 1.5 into 10 raised to 8. So that would be 2 into 10 raised to 8. Okay, I am not going to go into the calculation. I hope you can understand that. Okay, let's move to the third question. Absolute refractive index of some material media. We have given a table, and it is asking what is which material is highest optically density and which material has the lowest optical density. So as a rule of thumb, you can remember that highest optical density material have high refractive index, and lower refractive index material have low optical density. So diamond would be the highest optically density material according to this particular table, and air would have the lowest optical density. Okay, that's done. Now let's move to the fourth question. In which one light travels the fastest? So we know that refractive index is basically V1 by V2. We have defined it, right? So if the the first material is vacuum, we can just say it is N2. And the second material is the material that we want to find in which the light travels, right? So let's say diamond has very high refractive index. So what will happen? Okay, let me say that I will give this question to you, and you can do this in by yourself and tell me the answer in comments, or I'll just give the answer in the next video. Okay, now the last question is the meaning of, what is the meaning of this statement that the refractive index of diamond is 2.42. So the meaning of this statement is when a ray of light would hit a vacuum slash air diamond interface. So what is vacuum diamond interface? This particular interface. Let's say this thing is diamond. This particular drawing is diamond, and this would be the interface. Okay, this would be the interface, and this interface, so when light hits this interface, the ratio of sine of incident angle, right, and from the normal, and the sine of refracted angle from the normal is equal to 2.42. So that is basically the meaning of diamond having the refractive index of 2.42. I hope you guys understand it, and we can also define it this way. Thank you so much.